Okay, go for it.
Good morning. I welcome you all to the study that we're going to have today on what is science. It's basically connected with creation and evolution. Let me introduce myself to you. Who am I? My grammatically correct name in Sanskrit is Surendra Babu Sammeta. I was always ashamed to explain the meaning of my name, Surendra Babu, because it is a blasphemous name, meaning Father of God of Angels. Only recently I heard a second meaning to the name, and that is voice of God or voice for God, and I like it because a few months ago I made a commitment to be a voice for God for the rest of my life. I have a burden for young people who are confused about God and the sciences they learn at school, especially theory of evolution. So I wrote a book critically evaluating both the theory of evolution as well as intelligent design narrative. The book is in editing stage now, and I hope to publish it soon. India is traditionally a religious country, home to Hindus, Muslims, Christians, Buddhists, Jains, Zoroastrians or Parsis, Sikhs, Baha'is, and Jews, among whom all except Buddhists believe in a creator God, though the gods they worship are not the same God that we worship. Recently, there has been a movement among the young scholars in India promoting science in an atheistic perspective, teaching evolution as fact. My desire today is to reach out to the young people at school and college level and enlighten them on the two sides of the argument. Is evolution true, or is there a creator God? I will be in India through the month of September, and I'm preparing to make a presentation on the subject in at least 2 high schools there. My educational background, I'm a structural engineer with a bachelor degree in civil engineering and a master's degree in structural engineering. Among some 40 courses I studied for both of my degrees, I happened to study geology, astronomy, physics, including quantum theory, and higher mathematics, which are extensively used to support the evolution theory. My professional background, I have been working as an engineer for nearly 50 years continuously, except for 1 year that includes the months I was not employed. I worked as an architect engineer in my initial 10 years, and as a structural engineer for about 40 years on international projects. That includes 20 years in USA. I was involved in the design of high-rise buildings, industrial structures, structures connected with water supply and treatment plants. I worked as a senior consulting engineer for the government of Libya, and also as a senior engineer for the Finnish architectural consulting firm, supervising the construction of a whole city off the coast of the Mediterranean Ocean. I have a professional engineer's license in 5 states of United States, though I have also designed projects in several other states as well, including Japan. So I know a thing or two about design, and I can readily recognize design and the hand of a designer wherever I see it. These are my credentials, and with this educational and professional background behind me, I now venture to make this presentation. A word about my cultural background. I come from a country with extreme diversity. Diversity of religions, languages, races, and cultures of very rich people as well as the poorest of the poor, yet one sovereign nation. I have grown up to live in harmony with everyone there and that has become a part of my culture. I respect people of every nation, color, race, religion, language, and economic status. So today, let us study what is science. Science is used extensively in our life. And so let us see what is true science and what is not a real science. To begin with, let's have a short prayer. This is going to be a Hindu prayer. Let me read the prayer. It's in a little sing-song way. Asatoma sadgamaya, tamasoma jyotirgamaya, mrityorma amritangamaya, shanti, shanti, shanti. This is a prayer every Hindu prays every morning, beginning from a young child to the high priest. Most of you are probably shocked or offended at my making a Hindu prayer in a Christian temple, but I think if you know the meaning, you'll find that it's actually a good prayer. Let me show you the meaning. Asatoma sadgamaya, I am in delusion, lead me to truth. Tamasoma jyotirgamaya, I am in darkness and ignorance, lead me to light. Mrityorma amritangamaya, I am in death, lead me to life. Shanti, shanti, shanti. Peace, peace, grant me peace, O Lord. Well, this is the prayer every sincere Hindu prays, and actually this is the prayer that rings in the hearts of every sincere human being, because we all realize that we are in delusion. Although we think we know a lot, we are in darkness, and we realize that we are in death, and we need life. So the answer comes to us for this prayer through Jesus Christ. Jesus answered and said, I am the way, I am the truth, and the life. John 14:6. And we long for peace. And this is what Jesus says. Peace I leave with you. My peace I give to you. Not as the whole world gives, do I give to you. Let not your heart be troubled, neither let it be afraid. John 14:27. So what I'm going to cover in this series. Today, this first hour that we're doing, we want to deal with what is science. And the second hour, science and evolution. Next Sabbath, the first hour will be studying science, design, and chance. And in the second hour, we'll be studying science and the designer and his identity. Somehow there is a feeling in the minds of many that science and religion are antagonistic to each other, but they are not. True science and true religion are complementary to each other. Let us find what true science is. Now, mathematics forms the foundation of all sciences. Mathematics deals with numbers and their relationships. Here are the properties of numbers. Their values and relationships are constant. Values of numbers will never change. They are everlasting and consistent. Values of numbers are same everywhere. That means they are universal. Whether it's on this earth or on Mars or on some other planet somewhere in the universe, their values are same. Now, if you see $4,999,999 $5.99. Maybe very, it may look very nearly equal to 5 million. And for all practical purposes may be considered equal. But in truth, they're not equal. This shows numbers help to determine accuracy, true value or truth, correctness or rightness, in other words, righteousness and perfection. Just think of these properties of numbers, namely constancy, consistency, foreverness or everlastingness, universal, accuracy and perfection, correctness, rightness and truth. I put a picture of that light bulb, and wherever I have that, please keep this in mind. We'll come to it in future, in the future series. So let's remember those properties. Because of all those properties of numbers, it has become convenient to develop various branches of mathematics, like arithmetic, geometry, algebra, trigonometry, and calculus, etc. Numbers and their relationships play an important role in all sciences. Mathematics govern physics, physics govern chemistry, and chemistry governs biology. Now, normally graphs visually show the relationship between numbers. Graphs show how numbers relate to each other. If x and y are two unknown numbers and are related by equation y equal to 2x plus 1, we can give any value to x and see what will be the corresponding value for y. So in that equation that I gave, let us substitute values of x as 1, 2, 3, and so on, and see how the value of y would change. Now, if you put 1 for x, y will be equal to 2 times 1 plus 1, that will be 3. Or if you put the value of x as 2, you have y equal to 2 times 2 plus 1, that will be 5. And so on. You can keep on changing the values of x and then find the corresponding values of y. Now let us plot on a graph the values of x on x-axis and the corresponding values of y on y-axis. If you do that, you will find points as shown by those stars. They'll be all lying on a straight line. So we say the relationship between those numbers in that equation is a straight line relationship. Similarly, if you give various values for x in the following equations and find the corresponding value of y and plot them in a graph, you'll find the relation between x and y in very beautiful shapes. For example, y square is equal to 4 square minus x square. Let us keep giving values of different values to x, like 1, 2, 3, 4, and see what happens to the values of y. And take those two sets of values and start plotting them in a graph. Then if you see on x-axis horizontal and y-axis vertical, and you plot them, and then you get a circle. And similarly, solving this equation, y square equal to 2 square times 2 minus x square divided by 4 square, and plot it, you'll get an ellipse. Now you must have heard of Fibonacci numbers or Fibonacci equations. Here is an example. Here you have a rectangle. You have a short length here and a longer length for the rectangle. You take the shorter side of the rectangle and make a square in that. You'll be left with a rectangle which is exactly proportionate to the original rectangle. And again, you take that shorter side and make a square here. Then you'll be left with a rectangle which has the same proportion as the original rectangle. So you can keep on dividing the rectangles into smaller and smaller ones. Then you start connecting the corners of all these squares. Then there will be left, that will result in a beautiful spiral curve. And if you see the galaxy here, the spiral galaxy, we see exactly the same kind of spiral, a spiral curve. Now these are, they satisfy the Fibonacci equation. Now let's see one more. Here we have some crystals. Crystals are formed by molecules arranging themselves in a particular lattice according to the physics, according to their attraction, and it's all governed by the forces there. It can form only certain shapes. The salt of each mineral will form a particular shape. And this is where numbers play a role. Okay, the spiral galaxy and the crystals are two examples of non-living things. Now if you go to the living things, even here you'll find that those Fibonacci numbers and those equations, they play a big role in the shapes of these chambers. For example, this is a Nautilus shell, and all the parts of that shell are made according to that golden mean dictated by Fibonacci number. Yeah, here is the flower, all the petals and the stamen and all the parts of the flower here are they're according to the Fibonacci number in that pattern. So you see in nature how mathematics work, the numbers work. And I think you're all aware of this one. This is the DNA coil, double helix. Even this satisfies the Fibonacci equation. And so we find that numbers play a big part in every aspect of science. You must have heard of fractals. Now fractals are numbers that produce very complicated but beautiful graphs for simple equations. You can browse on your computer or your YouTube for fractals. Then you can see beautiful patterns created by computer solving those very simple equations. Also, I would recommend you to watch a presentation by Jason Lyle by just typing in your browser fractals by Jason Lyle. Let me show you some interesting graphs of them. So here are some graphs generated by the computer just solving some simple equations. Let me just scroll through and show you a number of them. Basically, these are relationship between numbers which are drawn as a graph. Okay? Now let me go back to the presentation. Now, here is one more graph done by the computer. This is also a fractal graph. And if you see in nature, you can see that the same fractals in play. Now, this is a ornamental cabbage, where you find that somehow those fractal equations are dictating the shape of those petals. And here is broccoli. And here also you see a three-dimensional representation of a fractal equation. So throughout nature, in whether it's living things or plane diagrams, you always find that numbers play a big role in them. Now, numbers in nature, we all know that there are 7 notes of music, or 365.25 days in a year, or 7 days in a week, 7 colors in a rainbow, 4 basic molecules in DNA. We have clearly seen how mathematics plays a role in the physical shapes of not only inanimate objects, but also the shapes and properties of chemicals and living matter. Now let us see what are the kinds of mathematics and sciences. We have pure mathematics or pure sciences. These are studies of fundamental mathematics and scientific principles and laws. Then they have empirical sciences that deals with science based on experience, experimentation, and observation. And then you have applied mathematics and sciences. These sciences apply existing scientific knowledge to develop more practical applications such as technology and inventions. And that's why applied engineers are called applied scientists. And so also anyone who deals with existing scientific knowledge and develop other practical applications, they're called applied scientists. And by that definition, doctors, nurses, the various mechanics, technicians, all of them can be clubbed under the same group, applied scientists. And if you apply the definition correctly, I think there are almost all of you will fall into that category. If you have done any cooking at any time at all, I think you are applying the knowledge of your knowledge of heat for making some interesting dishes. So I think now we are probably in a scientific forum. So we are going to discuss as fellow scientists and understand what is real science. There is also science called theoretical science or theoretical mathematics. Now let us see what the theoretical mathematics and sciences are. These are based on theoretical ideas or assumptions, but the results are not definitive. Assumptions are hypothetical ideas, and the answer you get is not as definitive as 3 plus 3 is 6 is a definitive answer, but not in theoretical mathematics. For example, they assume an imaginary number called I, which is equal to square root of -1. Now it's impossible to visualize a number that by multiplying by the same number you can get a minus value. But that's why they call it an imaginary number. But this is a clever assumption. It helps when you have several roots or answers possible. We'll get real answers whenever we have when I is raised to an even powers like I square, I raised to the 4, etc. But whenever it is odd number, we'll get a very imaginary and false root. Now there is another science called, under theoretical sciences, it's called in mathematics, statistics and theory of probabilities. It is used in predicting results such as chance of winning a lottery or in predicting population growth, etc. And in string theory, they assume about 11 dimensions, which is not physical. We cannot imagine more than 3 dimensions, which are length, breadth, and height. Now, talking about probabilities, if there are 2 people who are tossing a coin to decide who gets the prize, the chance to win is 1 in 2. If there are 10 people who are drawing lots for a prize, each one will have 1 in 10 chances of winning. In the first case, we have 1 prize and 2 odds. And in the second case, we have 1 prize and 10 odds. If the draw was made 10 times, you may not still get your name drawn even in 1 time. So this is a possibility. Although it says they have 1 in 10 chances of getting your name drawn, it's likely that even if they have drawn 10 times, there is a chance that your name will not be drawn even 1 single time. So higher the number of odds, smaller is the chance of winning a prize. Thus, in theory of probabilities, there is no way of getting a definitive answer. In theoretical science, your solution will be as good as your assumption. You may get a good answer or a correct answer if your assumption is good. Or you may get an approximate solution or a 20% correct solution or even a 0% correct solution, which means a wrong answer if your assumption is bad. Now let us understand theories and laws. Many students do not understand the difference between scientific theories and scientific laws. What are theories? Theories are seemingly reasonable and logical explanations for what we observe in nature or in more focused scientific experiments. When theories are proposed based on some experimental observations, peers examine the observations and the proposed theory. The peers then may accept it as reasonable or accept with amendments or propose an alternative theory altogether, or may totally reject the theory. So theories get revised or amended or totally rejected whenever newer evidences or observations are made in the future. Examples of theories: Einstein's theory of relativity and theory of probabilities used in mathematics, theory of evolution. These are all theories. They are not facts. They are not established by rigorous scientific methods. Now, what are natural laws? Laws are proven observations that can be demonstrated to be correct over and over again. They may start as a theory in the beginning, but when these theories are proved right by repeated experimentation and observations, then they get to be called as laws. Examples of laws: Newton's laws of motion. It has three laws: the law of inertia, the law of force, the law of reactions. And this is what engineers, whether he is a beginner or really a rocket scientist working on rockets and spaceships or the submarines or whatever, the more complicated structures, he uses just those three laws. Maybe just a few more, but these are basic for all engineering. Then you have Kepler's laws of planetary motion. Just to explain to you, the first law says all planets travel in elliptic orbits around the sun. So all the planets travel in an elliptic orbit. The Earth orbits the sun in an elliptic orbit, and the moon orbits the Earth in an elliptic orbit. It's all true, it has been proved. But fortunately, Earth makes the ellipse is nearly circular. It's closer to a circle than an ellipse. That's why our temperatures, and they're all moderate. If you have a big, very pronounced elliptical orbit, then when we are very far from the sun, the winter too cold and it can affect life. Or if you get too close to the sun, it can get too hot, and even that can affect life. So, and we'll proceed. Then for another example of laws is laws of thermodynamics. Law of conservation of energy, which simply means energy can neither be created nor destroyed. It can only change its form. The second law of thermodynamics, the terminology is a little complicated. Let me tell you in simple words. Things in nature continuously keep decaying. They will never get better. Okay, now kinds of sciences. There are many other related sciences like geology, medical sciences, material science, crystallography, astronomy, etc. But let us study today in some detail the basic science of physics and see how mathematics plays a role in it. After that, we'll make a very quick run on chemistry and biology. And since we don't have time, we'll be spending a little more time on physics only. Physics. Physics is a... Pardon?
Stop there for a minute.
Physics. Physics is the study of properties and laws governing the behavior of physical matter. It deals with interaction between three fundamental entities, namely matter, which means mass and represented by letter M, space, in other words, it's distance, represented by the letter L, and time, represented by T. All equations or forces in physics can be expressed as interactions between the above three entities. For example, velocity is distance traveled per time, like miles per hour. So it's dividing distance L by time. And acceleration is the change in velocity, which is distance traveled, distance divided by time. So it's L divided by T divided by T, and so on. That's how we can define momentum, force, G, which is acceleration due to gravity, weight, and we can also express energy, work, power, etc. in terms of mass, distance, and time. Now, let us study a little bit on structure of atom. For nearly 2,000 years, it has been believed that atoms were the smallest indivisible particles of matter. If you start chopping a piece of wood or whatever and cut it tinier, tinier, and tinier, you'll finally come to a small particle. You can't divide it anymore, and that is called an atom. But our understanding of atoms has started changing since the last 100 years. About 100 years ago, scientists predicted the structure of the atom based on mathematics and some observed physical properties. According to them, atom of an element was the smallest particle of an element with equal number of each having three more components called neutrons, protons, and electrons. Now the neutrons and protons clump together as one nucleus, and they're in the center. Then you have the electrons going around them like planets go around the sun. And this model is called planetary model. We have pictures of represented here of the atom. On the top left, you have the model showing a kind of a three-dimensional model. You have the nucleus in the center with neutrons and protons clumped together, and then you have the electrons revolving around the nucleus in all directions. The same model, you can show it in a two-dimensional form, which is on the right side bottom. You have that red spot in the center, the nucleus, where neutrons and protons are bound together. And then you have orbits shown in circles all around the nucleus. And you can also see one representative electron there, which will orbit the nucleus around that circle. And the electron will travel only in a permitted orbit there, which is based on the energy that electron possesses. It cannot exist in any position there. It has to have that particular amount of energy to be able to travel around in a particular orbit. When you increase the energy of the electron, then it jumps to the outer orbit, the next outer orbit. And you have to give a very discrete, fixed amount of energy to boost it up to the next orbit. And the same way, from the second orbit to the third orbit, you have to give the electron a very discrete amount of energy, and then it will jump to the third one. And if it loses energy, then it will start falling back into the level there where it belongs. Can we believe that that model is correct? These are all based on some of the theoretical mathematics. Using the theoretical mathematics, they proposed these models, and they believed that's exactly it behaves. And has anyone seen an atom? And I did a lot of search, and no one has been able to see a single atom in its place. No one has photographed, because it's practically not possible at all to photograph an atom or an electron. So they used a computer to graph. It actually measures the field, the energy fields around that atom, and then it translates through the computer into a picture. And that's what they did in that blue picture you see on the top right. And so when I saw that picture, I was really excited and happy that, mathematics, after all, the theoretical mathematics is really dependable, because the picture came out exactly like the theoretical model. And I just jumped up and down, so excited and happy. But it turns out that modern mathematicians, after doing some more study on the atom and its properties, they have come to the conclusion that the structure of the atom is not exactly like the planetary model, but it's more like a beehive You see the nucleus in the center on the left bottom, and they say the electrons just make local circles around it, not around the nucleus, but to a side of different sides of the nucleus. Just like the bee goes to the beehive and dances in circles to tell the other bees where the food source is. Just like that, the electron makes a little dance around the one of the axes near the nucleus. And also they showed that they call it a dumbbell shape because if you take two opposite of them orbits, then it looks like a dumbbell. So I keep thinking, is theoretical science, theoretical mathematics foolproof? I guess not. The picture they made, the blue the picture, what they call quantum photograph, I don't think they have done intentionally to cheat us, but they use their theory and they program the computer to catch the energy levels in that pattern, and that's why it did that. So what conclusion I want to draw here is that we cannot rely on theories and theoretical concepts because they're only approximate. They can be correct, but they can also be wrong. Okay, let's proceed to the Newtonian or Isaac Newton's physics. The forces in all matter, from atoms to the stars and galaxies, were believed to be following general laws of physics enunciated by Newton and other scientists from 400 years ago. But our understanding of the nature of matter began to change since quantum theory was developed around early 1900s. Einstein's theory of general relativity did not explain all the known laws. All the existing theories could not explain all the anomalies they found in nature. So the scientists went after search for a theory that explained all the anomalies. Thus was born quantum theory in early 1900s. Then around 40 years ago, string theory was developed to solve the problems quantum theory could not solve. Now, quantum theory, why am I talking about quantum theory? Are these really essential? Am I just talking about some things that we do not understand? But hold your peace and pay a little attention. You'll know later why I'm trying to teach these things to you today. Quantum theory is also called quantum physics or particle physics or wave mechanics. It has different names, but it deals with particles smaller than atoms, which are protons, neutrons, and electrons. The problem was to find a uniform theory that explains the four basic forces that seem to control the behavior of these particles. Now, what are those four basic forces? The strong force, the weak force, gravity, electromagnetic force, and I'm not going to explain because it's not necessary, I think, but scientists theorized the existence of other subatomic atomic particles that could explain these forces. So new particles. That did not explain every one of the basic forces, so they predicted existence of even other smaller particles like Higgs boson that explains why particles have mass, and particles and forces like muons, gravitons, gluons, neutrino, tau, etc. Now, there is a picture of a bulb again, so try to keep in your mind what I'm going to say now. Quantum behavior of particles. Particles behave like matter. Particles behave like matter when observed. Matter particles. Particles behave like particles of matter when observed and as waves of energy when not observed. They look like matter when you're looking at it, but as soon as you do not pay attention to that, it starts behaving like a wave, which means particles seem to have some kind of understanding whether you're watching them or not. They seem to have some kind of a knowledge, and that is really spooky. We think it's inanimate object, but what the scientists are telling us now from this quantum theory is that particles behave in different ways depending on whether you're observing or not. And they call it quantum wave particle duality. Another property, a particle can exist. We're talking about particles which are smaller than atom. Anything above the size of atom, they behave like normal, according to normal physics, the properties that we generally know. But when the particle is smaller than an atom, the subatomic particle can exist at multiple locations at the same instant. That means it can be present in different places, maybe one, if somebody has to keep track of it, your friend in Springfield must be watching it and say, yes, I can see it here, it's here in Springfield. And a friend of yours in airport here in Joplin, he may be looking at it and say, yes, right at this moment it is right here. And you'll find it right here because you are observing it here. And that is again a very unusual property. And that's why we call it a spooky behavior. And the third behavior they said is every particle has a conjugate or a companion particle which may be miles or light years away with which it is entangled. If you disturb one of them, its companion will react the same way, the same instant. Which means if you disturb one of the pair of the particles, if you give it a twist or a spin, its companion miles away or light years away will spin in the same direction at the very same instant, exactly at this very moment, it will be behaving the same way, which is again a very difficult thing to understand because according to Einstein's theory, nothing can travel faster than light. And so, even if you have to send a signal, it can go by a radio wave, which is the same speed as light wave, all radio wave, microwave, all these waves, X-rays, they're all different forms of light, so they have the same speed. So if you want to send a signal to your Mars lander, it takes about 45 minutes. If NASA sends a signal to them, to the orbiter there, it takes 45 minutes for it to give a command there to either move to the left or right or increase speed. And all these things will take time. So according to this third particle nature, it's very difficult to imagine how it can how it can do instantly, which is actually breaking the generally understood property of light, the light. Now, fourth property is particles can pass through solid barriers. They call it quantum tunneling. These spooky ideas based on errors, I'm just imagining, are they because of some error in the mathematics or not? But scientists are so sure of their math and believe these properties are so real that they're spending billions of dollars on research to find experimental proofs. And if they really find proof of this behavior, what will they gain from these properties? Because if that is true, if any of these properties is true, they'll be able to make computers hundreds of times faster and more powerful and much cheaper supercomputers. So they can put them in your cell phones. They can also make very high level of artificial intelligence. There's a lot of fear for artificial intelligence. Many great scientists, they have said artificial intelligence is dangerous. We should be very careful if you want to invent this artificial intelligence. But I think in about 1 decade's time, these scientists are going to probably prove some of these properties are real, and they may be able to use them to create this new supercomputers. And if there's no control, they might even do this artificial intelligence. Some serious scientists do not accept quantum theory because it does not explain everything. So they came up with a theory called superstring theory, which they believe unifies all theories and explains everything, like the various forces in atoms, the Big Bang, the black holes, etc. Now, what does superstring theory teach? Superstring theory says all matter in the universe are nothing but infinitely small vibrating strings of or filaments of energy. They're so tiny, trillionths of a millimeter in their size, and that's what they say. And if what they say is correct, then each of us is a bundle of vibrating strings of energy. I just want you to keep this thought also in your mind, because we'll come back to it later. Here's another picture of, I think these are all not real photographs or anything. These are the artist's way of explaining what superstrings are. String theory assumes 10 literal dimensions. String theory math shows extreme symmetry in matter, what they call supersymmetry. The theory is still in development. So maths governs physics, and physics governs chemistry, and chemistry governs biology, as we have shown in those beautiful illustrations on fractals, Fibonacci numbers, etc. However, mathematics or science cannot explain the spark of life or what causes life. And to prove any theory, scientists have put together a method called scientific methodology. And what they do, the method goes like this. First, we have to define the question. Then we have to gather information and resources pertaining to that question. 3, form a hypothesis. Then perform experiments and collect data. And once you get all the data, then you analyze the data. And then you interpret the data and draw conclusions that serve as a starting point for a new hypothesis. And then you publish results. But there are limitations of science. Scientists have studied in detail a lot of things concerning living beings, how their minutest components like DNA functions, but have not been able to explain what life is or create a living cell from scratch. Recently, two scientists made a list of 42 questions for which there seems to be no answer yet. And there may not be answers for a long time to come. Questions like, what is life? What is consciousness? What was there before the Big Bang occurred? What was the singularity that exploded at Big Bang? What are black holes? What is light? Because till now, nobody seems to know what light is. So as we wrap up, let us go back and look at a summary of our study today. Numbers possess amazing properties such as constancy, consistency, universality, accuracy, etc. So they can define perfection, truth, justice, correctness, rightness or righteousness. Number two, numbers or mathematics govern the laws of all sciences like physics and hence chemistry, biology, etc. Now, all sciences must satisfy mathematical laws and must be vindicated by mathematical evidences. 4. Pure mathematics and pure sciences deal with established facts. They give solutions that are deterministic. Whereas theoretical sciences deal with hypothetical or assumed inferences that have not been proven. Their solutions could be approximate but non-deterministic or undefined. Theories are seemingly reasonable explanations of some observations that have not been proved yet to be facts by unalienable proofs and evidences, whereas laws are proven facts. Theories are subject to be amended, changed, or totally discarded as new observations are made. Theories are not to be misconstrued as facts just because of the many times it is spoken of or because of the fame of the artists, the scientists who support it. Absolute repeatable experiments and proofs are required before a theory can be accepted as a fact. For a scientific theory to be accepted as viable theory, not only mathematical proofs but scientific methodology must be employed for the study. 8. Some scientific theories have severe limitations because of the impracticality of experimentation and application of scientific methodology. One may need to employ judgment based on clear logic, history, and predictability of an event. Most false information comes from not so accomplished scientists who are hype masters, who publish news in a sensational way to make theories look like proven facts. Beware of what you get from the media. Theories and our understanding will not be complete until we have found answers to some of the fundamental questions like what is life, what is consciousness, and other long pending questions by scientists. And that concludes our presentation.